to this computer. All right. Welcome everyone to our Oberlin Acoustics First Fridays seminar. So we will have a new topic every first Friday of the month for the next couple of months. And so welcome everyone. And our first speaker is Dr. Jesus Torres. He has a PhD in acoustics, and he teaches at the National Violin Making School in Mexico. So he works closely with both the students, and he's doing research into acoustics. So Jesus, would you like to start?
Okay, thank you, Fan. Thank you for the invitation. To you, Fan, Claudia Fritz for the support also, and many other researchers like Colin, Jean Woodhouse, answering specific questions over the years. Ivan Davis, of course, George Topani, I mean, and some researchers reviewing my papers and rejecting or accepting. It improves this research and many others in our acoustics lab. And thank you everyone to be here. Well, this is the title of the project, Tonal Copies of the Titian Stradivari Violin, employing multiple scientific methods. My name is Jesus. You are seeing the abstract that you received in the invitation via email. And this project was sponsored by the University of Mexico and from Música, Arte, Cultura Foundation. So let's start. Okay. Several data is available about the physics of the violin, the behavior of the instrument. We know a lot about most shapes of the free plate, of the most shapes of the body on the complete instrument. We have a lot of data. I mean, when I say we, I mean all the world, the human being, frequency response functions in terms of bridge mobility, radiativity patterns, directivity patterns, corpus mobility. We have computational models, theoretical models, analytical, numerical, finite element models, and more recently, we have more information about subjective evaluations. But I think that we have a lack of papers employing this information in the workshop. I mean, well, it's hard to find, at least for me. Of course, we have the Martinez-Lesque papers at the end of the 90s, where he named the tonal copies to violins, where he was trying to copy the sound instead of only aesthetical details. Maybe there are more projects employing this kind of information and saying to us, how is the performance in the finished instrument? So this project was focused on trying to use this kind of information in the workshop. Okay, defining the copies, we select the Titian as the reference because it's the violin more studied, I think, of all the violins. I found this paper of Frederick Sanders from 1946 with data measured in the instrument. And I think that Sanders measured the Titian in a previous paper But over the years, the Titian has been reported in several different kinds of papers. And in 2010, we have this project, the Stradivari project. And as you know, in the DVD, we can find a lot of information of this violin. We have CT scans, map thickness, sound recordings, subjective evaluations, high resolution photographies. And I think that in 2013, Michael Pirkos published in his thesis a finite element model based on the Titian using reverse engineering. So he estimated the properties of the Titian and many other research about this particular instrument. So, but we need to state clear limits. So the vibratory considerations were fixed in tuning the frequencies of the signature modes. Well, we are handling that the mode shapes in this low frequency region is tuned. I mean, the mode shape is the same if you are using, well, almost the same if you are using classical measurements and classical materials. So the project was focused on tuning the frequencies of A0, CBR, and the B1 modes. Fortunately, in the DVD of Stradivari, we have the data sheet including the vibration measurements in Titian. In this way, we can compare directly the data of violins and data of Titian. Okay, only the thickness of the plates was intentionally adjusted from the original design. It means that the arching profile, the contour of the sound box, all the dimensions were copied from the original instrument. Well, from the measurements of the original instrument. And only the thickness was adjusted. Additional considerations, aesthetical details. Even when our main goal is trying to tune the frequencies of these four modes, of course, we want to see the same color and the same shape of the original instrument in all 5 violins. So you can see the results in this slide. We have 5 violins with the same color. Well, this is our interpretation or our capabilities to copy an instrument. And we try to copy the arching profile using the CT scans extracted from the original instrument. You can see the files. Do you see my arrow, my pointer? Yes? No? Well, in the left part of the slide, you can see the CT scans.
We can see your cursor.
Okay. Okay, we have two kinds of copies. Traditional copies and computer-assisted design copies 2 and 3. Okay. The 2 traditional violins were designed trying to tune the mode 2 and mode 5 of the free plates, having pre-established frequencies. Unfortunately, we don't have the frequencies of the free plates of the Titian. but we need numbers. So in this table published by Joseph Curtin in the Strat magazine, you can see some data of Stradivari violins. So we choose the Wood Stradivari violin as the reference for the free plates in the Strat violins, only because it was made 1 year later of the Titian. Maybe it's not very scientific procedure, but at least it's pretty clear. So we need to copy, to obtain these frequencies in the plates of the two Strat violins. And the history for the backplate is even harder, because it's a hard task to obtain the free frequencies of the backplate from all the Italian instruments. So one more time, we ask information to Joseph Curtin without any responsibility for Joseph, of course. And he said the text that you can read. Mode 5 between 350 and 380 hertz, and weighing around 105 grams. So we take it. The three finite element violins were designed in a very completely different procedure. We used a model published last year in the Journal of the Acoustical Society of America, where we proposed a finite element model of the Titian with a particular feature. We have a lot of finite element models of violins. We have the model of Colin in console, the model of Santa Maria, I think, in Abacus, the model of Michael Pircos, I think, in Abacus too. But what is different in this model? This is a parametric model. Surely, the model of Michael is better, is closer to the Titian. But in our model, you can change the geometry quickly. So the procedure is as follows. In the paper, which is free, I don't know why we don't pay anything, but the journal put it for free, I don't know why. And with this paper, you can download also the model in a text file, in a text file that you can see in this slide. So you download the free version of ANSYS for Windows. You take the code, the file of the code, press read input from, and you obtain, well, you present it, of course, and you obtain the simulation of the mode shapes and other simulations. Now, if you want to see what happens if the Titian model has not bus bar, Eric Hansen is requesting remote control of your screen. I don't know. You can regain control. Well, I will approve. I have a message. Approve. Waiting for Eric Johnson to control your screen. Well, it's Eric Johnson. He can do anything. Okay. Well, if you want to see the behavior of the model without bus bar, then you need to put 0 in this value of bus bar that you can see, and rerun the simulation. And now you have the simulation with bus bar and without bus bar. And you can change a lot of parameters, and you can see, you can do before and after comparisons. One of the things that you can change is the material properties, of course. So how a finite element simulation works, you need the material properties that you are using in your real structure and the geometry of the structure and mathematical equations done by the software, and that's all. You obtain the dynamical behavior, of course, through mathematical process. So it implies that if you have the material properties of your copy, you can estimate the performance of the instrument before to be made. How we obtain the material properties? Well, we extract the contour of the plate, and from the rest of the material, we create wood samples, and from the free vibration modes of the samples, we can measure the elastic properties and the density. You can see in these values the agreement between the model of the JASA journal and the experimental values measured, I think, by George Bissinger. Well, the data in the Stradivari DVD. And I think that the agreement is good. 413 to 410, and you can see the agreement. Oh, at this point, I need to say, in general, models in general in science are not created to predict the future. This is very important in this project. We're not trying to obtain, to see the future. The models in science are created to gain a better understanding of the phenomenon that you are studying. What happens if I take one way or another way? In this way, you interact with several factors not considered by a simple simulation, but you have a big picture of the behavior, which is pretty useful in the science and in the workshop in the history. Okay, the material properties, this is the table. You can see the density, elastic modulus, shear modulus, and radiation ratio. So we have 2 trap violins and 3 finite element designed violins. The cloud is saying that subscript was related to radiation ratio of spruce. So trap low means traditional violin with low value of the radiation ratio of the spruce. But for a quick reference, high means lower quality wood, higher quality wood in the spruce. So Feb low, Feb me, and Feb high is finite element violin with lower quality in the spruce wood, medium quality, and higher quality. But well, you can see the values, and you can guess the quality of, I suppose, the quality of the wood with this table. So table 2 shows the calculations for several steps. In the first row, we have the values calculated and the experimental values of the Titian, the target values. And in the second row, we have the first simulation for the Feb low. In the first configuration, we have the top plate using the Titian thickness and back plate using the Titian thickness. Running this simulation, we obtain very low frequencies, as you can see. In the CBR mode, for example, 410 to 386, the tune. In the next simulation, we have the top plate remaining with the same thickness of Titian, but the back plate is thicker now. And you can see that CBR mode arises clearly the frequency, while the B1 plus mode, well, frequency is almost the same than the previous step. In the next step, we interchange the thickness. So now the top plate is thicker and the back plate has the thickness of Titian. For this configuration, now CBR, the frequency of CBR is lower, but the frequency of B1 minus is higher, clearly. We can say now that with the backplate, we are controlling the CBR frequency, and with the top plate thickness, we are controlling the B1 minus according to this basic simulation, okay? And B1 plus is remaining almost in the same value. So in the last step, we have thicker top and back plate, and we obtain the best agreement of the simulation. So you can see in italic numbers the best simulation for the 3 finite element violins. In Fed low and Fed medium, we need top and back plates. It was a surprise for us because it means that the denser wood, the thicker plate. I don't know if all of you know that. At first, it has not sense for me, because if you have, in my mind, if you have an all Italian violin, well, this is my violin. If you have an all Italian violin, maybe surely you have an instrument with very low values of density, and if you are trying to copy an all Italian violin, surely you will have wood with denser wood. So for my imagination, then we need, if I have denser wood, then I need thinner plate. But this is not true. So we take the suggestion of these simulations. In table 3, we have the experimental frequencies of the free plates. As you can remember, the target for the top plates of the traditional violins was the frequencies and weight of the wood Stradivari violin, 150, 345, and 58 grams. And I think that the match of our values of the trad low is good. But we need to choose or tuning the frequencies or tuning the mass. And we select the frequencies. And for the black plate of trad low, we take the suggestion of Joseph Curtin. And we obtain 364 mode 5 and 103 grams for the mass. The top plate of Strat High followed the same criterion, but to have a different violin, well, a different data for this violin and the Strat Low, we changed the parameters for the target. We changed the target for the back plate. Now we are only trying to tune the back plate, the frequency of the mode 5 of the back plate, as you can see. Here, 345 and 346. And for the finite element violins, we only have instructions like thicker than Titian or thick as Titian. So in this part of the design, we are joining knowledge from different sources. Of course, the experience of the maker reported data from other violins, suggestion of other researchers. For example, I can remember a table in the physics of the musical instruments book of Fletcher and Rosin. I can remember a table where Carlin Hutchins is saying that 185 hertz for mode 2 in a violin is a good frequency for a soloist violin. Well, when I talk about this topic in Oberlin in the last presidential meeting, all agrees with these values are high. It means the thickness is high. But all the time you can remove the plate and remove more wood if you want it. But with the configuration of the plates, as you see in the last slide, we obtain this corpus mobility. In table 4, you can see the data, but I think that figure 7 offers a big picture of the behavior. So in top of figure 7, we have the corpus mobility in black, in the black line of the Titian, and the corpus mobility of the Strat violins. At bottom, you can see the comparison against the finite element violins. Well, the real violins designed from the finite element procedure. And I think that the agreement is clear of the finite element violins. For example, let's see the last peak, the V1 plus peak at around 550 hertz. For the Strat violins, you can see that V1 plus is clearly the tune. The frequencies are lower, but also for the other modes, even the A0 mode is the tune. But in finite element violins, the tuning of the B1 plus is clear, and in B1 minus, and CVR mode. CVR mode is this peak around 410 hertz, and we have peaks around these values. And A0 is tuned also. So the conclusion of making these 5 violins, by following the procedures here explained, we can tune the signature modes with very different types of spruce and maple. Of course, higher frequencies must be also tuned, but it is a good start. So finally, I want to talk about ongoing projects. Some from finite element models. Okay, Again, we are not trying, well, we are not trying to obtain a realistic sound. Well, we are trying, but maybe we don't have the capability to do that. Instead of, we are trying to obtain, we are trying to perceive differences in sound coming from computational models. I mean, we take the values of a simulation of a particular violin, and then we inject a sawtooth waveform, a very simple, very simple model of the force of the bow string in the bridge. And we are injecting this force with this vector, this blue vector that you can see in the bridge. And that's all. We are performing a transient domain, a time domain simulation of this configuration. And in this way, we are calculating the sound of the G note. Again, you will hear the sound, and you tell me in the chat or talking in this presentation if you hear the differences. So I will play violin 1, violin 1, violin 1, violin 2. And let me know if you hear the difference. The sound was, okay. Now, violin 2, violin 2, violin 2, violin 1. So we want to link the differences, if such a thing exists, the differences with the configuration of the model, the design of the model. And finally, we're trying in projects with students, we're trying to obtain a do-it-yourself bridge mobility. In the blue line, you see a measurement using expensive devices. And in the black line, we are using equipment about $5 or $4 of investment. We're still working on it, as you can see. And finally, maybe my favorite project, a laser speckle interferometer using Lego blocks, the toys, and a laser pointer. We started working on it. And that's all. Thank you for your attention.
All right, thank you. Actually, Jesus, you crammed a whole lot into the beginning of the talk. There's a huge amount of information there that I'm probably not the only one that is still trying to digest the beginning of that talk, but I don't know where to begin, so I'm going to open the floor to questions now. We do have the option later of trying something. You know, I can create breakout rooms if we want to discuss some of these topics, and maybe different topics. You know, different people might have different issues they want to discuss, and we could create breakout rooms for that. So we're going to maybe get ideas for that in this initial Q&A session, and see where it leads us. So who wants to begin? We have a question from Dimitri.
I'm looking. Hello. Hello, Jesus. Nice haircut. Thank you. Thank you for a lecture. Very exciting work.
Thank you, Dimitri.
Well, my question was, yeah.
I need to say that Dimitri was the first guy trying to use the model. Well, one Sunday in the morning, I received a message from Dimitri saying, "Hey, why it doesn't work?" So, well, it's 7 o'clock in Mexico.
because I was trying to make a violin model here by myself with my friend physicist, and then I was exciting to know that you already successfully done it. So I was very happy to discover your work. So my question was, correct me if I'm wrong, reading the Mike Pirkost's work, I got an idea that he was able to recover the free plate modes from the CT scan information and he was measuring the factory violin free plate modes, then he was measuring the body modes of the factory violin, and then he got some correlation. So in my understanding, if we have a CT scan with geometry of the body, with thicknesses, with density, is it really a big problem to be able to get free plate modes from this information?
No, it's pretty easy maybe for Michael, but I don't find these values that you are saying. If you have the properties and the geometry, calculating the plates is pretty easy. But I don't know in Abacus, in a parametric model, it will be pretty easy. We are doing this all the time because you only remove the parts that you are not needing, but I don't know in Abacus. In fact, Michael uses another violin to calibrate finite element model. And then when his model is working, then he takes the geometries of the Titian, and from reverse engineering, he was estimating the material properties. But these material properties estimated by Michael works in his model. We take the material properties for our model, and it does not work for our model. Because we are not having exactly the same model. So we need to change the thickness of the ribs. And well, answering your question, it's possible, but I don't know if he is interested in doing that. I mean, maybe only he handling his model can do it. Okay.
Jesus, can you explain why his data, the two data works in one model and not the other? It's confusing to me.
Okay. Michael was using a scan of the original model. Yes. I mean, he has a closer violin to the Titian, a closer model to the Titian. In our model, we sacrifice the close relationship with the original model to do a parametric model. For the parametric curves that we need in the violin, we need softer curves to obtain this control in the model. Yes. For example, we need ribs of the same highness in our model. In the model of Michael, he is using the different highness in the ribs. It's very impressive. So these small differences finished in different models at the end of the history. So the hardness part to simulate is the properties of the ribs. He has an estimation of the properties of the ribs, which does not work in our model. So, what model is to serve to the people. So you can change the model in terms of obtaining a model useful in your particular research. Yes, so we have different models.
Yeah, so can you clarify? Because when you say it doesn't work, do you mean that you can't actually use the data, the computer program doesn't run, or
No.
that the results don't match the physical measurements on the instrument?
The results are not match, are not making a match. For example, in particular, as you can see in my presentation, I show this table too, and I try to explain that B1 plus is not changing. Yes, the frequency of B1 plus is not changing if we are handling the thickness of top and back. The changes in B1 plus does not exist, for example, is one way to say. But using the material properties of Michael for the ribs, we obtain B1 plus frequency around 600. And the typical shape of B1 plus disappeared. It was a problem for us. And a reviewer of the paper, Colin, correct this part saying that it's unacceptable, your simulation of B1 plus. So we need to correct and understanding why it does not work, okay?
Okay, Jim Woodhouse has his hand up. Maybe he has some insight into this.
Yeah, well, I was, absolutely thinking of this same thing. I mean, I think you've raised a really important point in this talk, which is kind of under the surface in the discussion you've just been having, that quite a lot of people trying to develop a finite element model or whatever of a particular instrument regard the purpose as being by hook or by crook to match that particular instrument by fiddling the parameters in whatever way is necessary. You've done something much more interesting with your parametric model because of the sort of things you're just raising, that our models, we never quite know enough for the models to be right. But the thing that you can use models for, and is very illuminating, and of course it's the thing that Colin did in all his epi work, is to look at the influence of changing things. And you would expect to get the direction and the sensitivity of changes to be correct and physically illuminating. And that's a much more interesting thing to do than to say, oh, but it's not 487 hertz, you know, it doesn't match this particular thing. So I'm very much supporting your agenda here, that the parametric model and then using the model, I mean, probably to document the kind of thing you were just talking about, to look at the how many percent changed. You change each of your parameters, including these rib property things, how sensitive, which things are sensitive and how much so. And that tells you both something about finite element models and perhaps something about which properties actually matter when you're in the workshop, when you're choosing wood. Maybe some of these mode frequencies are more sensitive than we expected to things that we often don't think about, like the properties of the ribs. People often don't document those. So I think you're doing something which is good here. And just to draw an analogy, because you had some sound examples, and I was talking about some sound examples in my talk last month. There's an interesting contrast in the kind of stuff I've done with simulation models and making sounds between what I'm interested in doing and what the music synthesis people are interested in doing. I want a model of a real guitar or whatever it may be. I want my model to be as close as I can get to the physics and then to see what it sounds like. And that's not at all the same thing as wanting a model that's vaguely related to the physics, but adjusting anything you fancy in order to make it sound good. But if my business was in producing resources for composers, then making something that sounds good is all that matters. They don't in the least care whether it's got the correct physics of the guitar behind it. They want something that works. So you see, it's a kind of similar thing. You can have a finite element model. You decide you want the Titian, you want everything as accurate as you can, and you fiddle things until it works. Or you can say, so what? Actually, what you want to know is about violin makers in the workshop or in the timber yard, choosing materials, making choices, making changes, and using these models to explore sensitivity. It's much more interesting agenda, and you ought to be applauded for going down that route, I think. So nice talk, thank you.
Thank you for your words, Jim. And well, we shared some emails about the sound of my violin sounding as a truck. In fact, we are pretty interested in where is this? For example, in the sound that you hear, I would play again, violin 1, violin 2. We measured that the main difference, as you can see in the spectrum of the sound, is the fifth harmonic. Even if the sound is like a trumpet or any other thing, but not a violin, even in this pure sound, we can see that the fifth harmonic is the main difference, at least below 1 kilohertz. So with the model, we are trying to discover how this fifth harmonic can be controlled. And we move many parameters, thickness, material properties, F-holes, several data. And we think until yesterday that the bus bar is the most important parameter in this transition hill around 1 kilohertz. But this is only a very, very preliminary result. But this is the capabilities that the parametric model can offer to the research or violin maker as Dimitri or many of the violin makers in this talk, trying to using this kind of model and linking with the first comment of Fan, maybe we can organize only one talk about the simulation, and if you have the ANSYS installed in your computer, maybe we can create some simulations together, if of course, if you want.
Just to follow up on that, I mean, if you're interested, I'd much rather give you resources and have you do the work than you send me things and me do the work. But in my talk last month, I talked about this sort of hybrid approach from Claudia's project. If you're interested, I can easily send you a WAV file of that, the violin snatch that I use there. So that's actual bridge force recorded on a real violin from a real player. What you would need to do to use that is to simply do one extra stage from your model. You need to generate the impulse response from your model at the bridge, and then you do a convolution of that with a realistic. It's actually fairly straightforward to do. You probably do a sufficiently high resolution frequency response and then an inverse FFT, and you'll get the sort of clonk sound of the violin. Then you could convolve it with a bit of real violin playing, and that might change your perspective on the kind of comparison you've just played us. Because in all honesty, if you hadn't told us it was a violin, we wouldn't have guessed, would we? You know, it's just the sawtooth sounds like a sawtooth oscillator. You need an input signal that sounds like a violinist. But then you want to use exactly the same input on all your different violins, and your comparison is then a fair one. And if you're interested in that, just contact me offline. I can send you some recordings of bridge force signals which essentially you can feed those into your simulation instead of your sawtooth?
Yes, it would be great, and we can try it.
Remind me, send me an email later, and I can send you some stuff.
It would be amazing. Thank you, William.
I think another.
Go ahead, Evan.
I think another simulation that may be shop worthy is do the impact response, because that can be done in the shop and tune up people's ears. I find that just hitting the clunk sound with the fingernail really starts makes it pretty easy for me to identify different instruments where playing them doesn't. And so I think there's a learning process there of listening to the clunks and using that as a diagnostic. My 2 cents.
Sorry, what is the question? I don't understand exactly. Sorry.
So Jim was talking about using a real violin force.
Yes.
To drive the model.
Yes.
I'm suggesting another sound that could be used to educate yourself on the sounds, different sounds of the violins, is the simple impact.
Well, so the simple impact is available right now.
Yes. I'm just saying that it's another one that if you're looking at a shop calibration thing, is there's an education process here.
Oh.
Can you hear the differences between these two instruments? Spectrally, what are the differences? I find listening to the clunks,
some napkins for us?
It's very easy for me to identify different instruments. So yes, you have it in your pocket. That's why I'm suggesting it.
But you say the key words in your words. For you, it's too easy to hear 2 different violins and tapping the bridge.
Right.
But you have a lot of years doing such a thing.
No. I try it at home. Jim showed me this a number of years ago, and I came home and tested.
I was hoping you got that from me. Yes. Now, yeah. Evan is a drummer. He can't hear violins, really. He just does acoustics.
Okay.
I quit.
Well, you can model in the way that you want, in a classroom or in a research or in Sunday, as Mitri, as you want. Thank you.
Hey, Jesus, I have a specific question, because on your 2 sound examples, I agree with Jim that if you didn't tell me, it's not obvious it's a violin. But on the other hand, I do hear very clear differences between the 2 sound examples. And you pointed out it's mainly the 5th harmonic. I'm also curious, what is the actual physical difference between the 2 violins? These particular 2 violins.
The properties and the thickness. In fact, there are these 2 violins. We have the violin 1 and violin 2, and
okay.
in one simulation we are using the properties and the thickness of this violin, and in the other properties and thickness of this violin. This is the difference. So we are trying to link this sound with these violins and trying to learn something.
Okay, thank you. Anders.
Yes.
Hi.
Interesting talk. I have 2 questions. One thing is it what kind of finite element code are you using? Is it Abacus or is it ANSYS?
ANSYS.
ANSYS.
Yes, ANSYS have a very nice option of not using the graphical user interface. You can access to ANSYS from commands. I learned ANSYS like.
Is it freeware?
Well, no. ANSYS is well, yes. ANSYS has a very powerful and expensive software, but they offers a free version with limiting the number of notes. They offer free 30,000 notes.
Okay.
30,000 notes for free. So our model is 51,999 notes.
Okay. Okay. That's a lot of counting.
If you put one note more, it cracks. It really doesn't work. But it's free. The answer is ANSYS, and it's free to run this model.
Okay, and then I wonder about the interferometric setup there. What are you up to with that? What are you going to try to measure?
Well, we are trying to obtain. Well, we are trying to replicate an experimental setup published by Thomas Moore in American Journal of Physics. He can obtain the differences of the speckle. Speckle is like a cloud of the reflection of the laser in a surface.
Yes.
So if you change the surface, the speckle pattern changes. So you can obtain a lot of information from analyzing the speckle pattern.
So are you using a pulsed laser, or are you using a continuous? Is it a pulsed laser?
Continuous. It's a pointer. That's a pointer.
Laser pointer.
Yes, it's continuous. But this setup is in the house of my student. So okay. he is using the not so powerful laser to protect his eyes. Yeah. But now that he has more practice, we can try with bigger laser to improve the speckle pattern and doing some mathematics. We want to obtain patterns in real time through the computer.
Okay.
Jesus, how much success has your student had? Because I actually spent a lot of time working with a professor from our local university on building this laser, and he pointed out that it's not as simple as the original paper made it out to be.
Well, that's true. We're trying to do this interferometer whole this year, and we are not obtaining very promising results until now. But we're still learning. We're still learning.
Okay.
I don't know. I don't know if Thomas Moore is here. In the last month with Jim, he's in the presentation. I don't know if he's here, but maybe I need to contact to him, because some details are very dark for me, because I don't know almost anything about.
Traditionally, those tables needed to be very well vibration insulated, and it could be stone tables with rubber inflated rubber under them, or it could be more professional controlled systems. But I've also heard more talk about this, and I think one of the points is when you have a pulsed laser, then you don't need to vibrate insulate the system because you have these pulses coming and the time between them is so dense that it should work anyway. So it's very interesting work there. I hope you succeed, and so we all can have a laser lab in our workshops in the coming future.
I have access to a laser, a pulse laser, but we need to learn more about lasers and these setups before to going to the lab in other universities. And my wish is that Said, my student, learn to use lasers, even without any powerful result. And then he can continue his master's degree using better installations, as you say, mercury in the you know that, yes. But this is only used as training maybe. But this is really fun, I think, and this is very important for me and for Said.
Yeah, I should mention to the those members of our audience who are not familiar with this technology is that it will enable you to see the vibration patterns of the violin, and you can see the mode shapes and everything. That's what it's useful for. So we have a question from Joseph Najivari.
Okay, thank you.
Hi. First of all, I welcome your undertaking, and I appreciate this work that you've been doing. Since the purpose is the creation of tonal copies, do you plan eventually to publish a musical scale on each violin and then set up maybe experiments like those done by Claudia Fritz and Joseph Curtin, where good players play through the violins for an audience who would then judge the success of the individual variations?
Okay, Jesus, before you answer this, I have to admit to something, because I changed the title of Jesus's talk slightly for marketing purposes. Tonal copies of the Titian Strad was not his original title. It was a slightly less, title that didn't try to claim as much. And but I thought this would attract more people to the talk. So Jesus.
Okay. Well, we hope that in the future we can obtain at least better tonal copies. But using this information for the hard subjective test that Claudia employs, it will be very hard for me. It's easier to ask the help of Claudia. So maybe in this project, say that Jim is saying that sharing data to obtain sound that he needs, well, all of us need, maybe we can start to construct the project that you are using, Joseph. Submitting this sound to people is maybe harder than creating the scale using the violins, the virtual violins. But maybe in the future, we can do that. I hope so. Thank you. Yes.
So I have, can you hear me? I have
yes, go ahead.
Additional comment. I have a recording of Cho Leon Ling, the owner of the Tiziano violin, who played a 2-octave chromatic scale at the Rice University Auditorium. If you are interested, I would be glad to share those files, and then you can compare the sound of your instruments note for note directly with the original.
Well, it will be great. Please do that. Yes, I read you. Yes, thank you, Joseph.
Okay, any other questions, Joseph?
No, thanks.
Okay, Anders?
Yes, thanks. I was wondering, those two violins, Jesus, you showed and you gave sound samples from, and you said that one of them is thicker than the other. Which one is it that has the weakest fifth harmonic there?
The thicker violin. the thicker violin.
Okay.
Well, we determined without a lot of strong basic idea that we don't want high harmonics in the 1 kilohertz region. Yeah. So we think that having lower harmonics in this region is better. So in this particular situation, thicker plate doesn't work for this harmonic, for this note, only for this note. Okay.
Okay. Is the sound sample coming from the finite element simulation in some way?
Yes. Well, the simulation was created thinking in one thing. We have a stereo configuration of the sound. In the left channel, well, in the left channel, we have the finite, the node of the sum hole, of the A0 resonance in this loudspeaker. So in the right channel of the stereo file, we have the behavior of the body. So in your speakers, in your stereo speakers, you are hearing as is the loudspeaker is the violin, not the sound, not the sound pressure in the air, no. The loudspeaker is the violin, so here we have the vibration of the air, and in this loudspeaker, the vibration of the plate, of one point of the plate. Is the better configuration. We are trying a lot of different configurations, and it was the best sound. Can you imagine? It's the best sound in this configuration, okay?
All right, Colin?
Your microphone, Colin, I cannot hear you. Yes.
Okay, hear me?
Yes,
Yep.
yes.
Okay, fine. Very nice talk and very interesting, and obviously I very much enjoyed the sort of work that you're doing at the moment. There are one or two little points. One of the things that really determines the frequencies from the modeling that we've done earlier is that at low frequencies, the arching is very important. I think probably all violin makers realize that. So sometimes it's not that surprising when you make changes in the thickness, you're not actually seeing the large changes that you might normally expect if you look at textbooks. The other thing is that, of course, the frequencies of those modes, and particularly the breathing mode, the B, which is involved in both the B1 minus and B1 plus modes, is very dependent on the interaction of the air inside the instrument as well. So that's another thing that makes the actual thickness of the plates less important than you might otherwise expect, thinking that it's just a simple thin shell type of model. The arching is very, with flat plates. The arching is so important. And the amount of arching, of course, affects the interaction with the air as well, because it's the rigidity of the plates that's so important. And the arching gives a lot of extra rigidity to the plates. And the last thing I'd like to say is, of course, that the sound post and the sound post position is all important. That you can make a lot of difference in the frequencies of the B1 minus and B1 plus modes in terms of the position of the sound post relative to, shall we say, the base foot of the bridge, just particularly the transverse position, that is moving across the waist, much less up and down. That's what the modeling says. And so when you're comparing different models, finite element models, is everyone using the sound post in the same place? And can you vary your sound post? Because it would be very interesting indeed to be able to hear the difference in sounds as you do so. It's much easier to do it on a finite element model than it is to do in practice because of the arching.
Okay. Well, the answer of your last question is, well, your last point, is pretty easy to do that in this model. For the way that we are creating the model. In fact, you can see here, sound post, because it is created parametrically. So you can change the position of the sound post through these simple values. You can move in the here in the top part of the text. You can see very basic indication of the axis in the plate. So we have the plate, the F holes, and the sound post is this mark. So if you want to move the post in this position, you need to change X, some position, Y, some position. But to avoid the problem with the arching profile, we need to change the arching profile at the same time of the sound post with some mathematics. Regarding to the arching profile, as you explained me in several times, the arching profile is very important. But in this project was very interesting because we need the restrictions of the workshop. So we need to create new violins. And if we need new arching profile or particular arching profile, increase the complex of the instructions for the maker. Instead of, if we only take the arching profile of the Titian, as you can see in this, no, okay. So the instruction for the makers was taking these plastic profiles and obtaining this arching profile. Changing the design of the arching profile, it would be great, but maybe, well, surely we need more steps for using this kind of information in the workshop. Okay, and well, several information of the design of the soundbox was learned with the real measurements and the continuous simulation of the data. Okay, so thank you for your points, Colin.
All right, George.
Do you hear me?
Yes.
Okay, it's great work. It's all nibbling away at the things that we don't understand, and again, it's a great idea to do it in the context of a violin making school, because you've already got a lot of the resources that you need at hand. There are a couple of things that I'm curious about. Is that you talked a great deal about frequency of signature modes, and not at all about amplitude. So I'm wondering, I would, as an opinion, I would say that the configuration of the signature modes, or at least modes below a kilohertz, certainly are a factor in how you perceive the sound of the instrument. But in contrast to that, I remember an example when Joseph Curtin, a long time ago at Oberlin, played some recordings of two instruments that sounded incredibly similar, but their radiations, well, at least the signature mode regions, were entirely different. And it was actually the envelope of the higher frequencies that gave us our impression of the tonal, or the timbre of the instrument, rather than that of the signature modes. So well, it's a complicated thing. Likewise, when you start playing around with material properties and plate thicknesses, you're sure you're shifting around the configuration of the signature modes, but you're also having massive effects in the Bridge Hill region and up there in areas where we're extremely sensitive to. So, I mean, is this a problem for you to look at that in the finite element models? You feel that you're perhaps compelled to work more in the low frequency region rather than seeing how it would play out in higher up?
In the original works of the tonal copies published by Martin Schleske, you can see how he was following in the signature mode, following the nodal lines. And he was using, I think, the MAC values to compare, or something like that, to compare all the mode shape in the whole sound box. So it implies that he was making the violin, measuring the violin, measuring the real violin, and comparing both values, which is a lot of work. So for this kind of comparisons, we have a lot of limitations. One very clear is that we don't have the complete data of the mode shape to be copied. We need all the data. We need all the data of the whole sound box to compare point by point. So before to control these mode shapes, we need to implement the procedure to compare mode shapes between two instruments. So this is one of the several reasons that we only put our attention in the frequencies. Of course, the amplitude and the particular shape of the mode is very important. And Bridge Hill is very important too. But we need to start with something. But I hope that in the future we can do that, George. Okay.
Well, it's certainly a bit of a fool's errand to try and control 100 or more modes in terms of all their properties, all the different parameters of those modes. But I mean, I say in some of Colin's work, he's looking at the function of the bass bar and the sound post, and modeling the overall envelope in the high frequency rather than the individual peaks resulting from particular mode shapes. Is that something that you can do in your model?
Well, when you're comparing only one point in all the response, because when you're talking about the Bridge Hill, you are talking about the response of one point over all the frequency range. Even to do that, even to tune one point of the bridge mobility in the other side of the bridge is very hard. Trying to tune only one point, it's too hard. So in the paper, you are sharing your screen. Maybe you are seeing my screen?
Yes.
Let me show you the paper. Exploring, this is the paper. In the JASA paper, you can see that we are changing the F hole's position as an example of the powerful of this model, of the power of this model. So we are changing the F hole's design in the model, and then we can move the Bridge Hill, as you can see in this response. All the frequencies, well, all the response in all the frequencies is the same except in the Bridge Hill. So the design of the F holes seems to control a lot the Bridge Hill. Well, in Mexico, we say something for this kind of affirmation. We say something like, we are not discovering the hot water. It means that all the research of Eric Hanson point to the F hole design. in the last years. So we are only trying to show how kind of things you can simulate in this model. But if you uses this information and put in a real violin, you could obtain a Frankenstein violin, yes, because nobody wants it was explained to me for Joseph Curtin, nobody wants a violin with F holes in a different position than the classical method. So trying to tune high frequencies is a very serious task, George. But we try to do in the future, of course.
All right. Any follow-up, George?
They're complicated questions, really. I don't think we can really get very much further on that. But I agree, obviously, single modes at high frequencies are going to be mostly impossible to deal with. And it's not really the point, is it? I mean, one is more looking at, say, lifting the response in a band rather than in an individual peak. It's okay. I'll leave it there. I think it's not helpful to pursue it.
Okay.
Thank you.
Thank you, George.
Claudia?
Yes, thanks, Roses, for your nice talk. I have a few questions. So first, about the sound. So you don't have any model of like no coupling with air. So your sound is just the vibration of the box.
Yes.
Yes,
we are not only from the sound box because it's easier and it has some sense. It has some sense to take the vibration of the surface in the vibration of the surface of the loudspeaker. It has sense for us and it's pretty easy, of course, than the simulation of the air.
No, sure. It's not a criticism. I was just checking that this was.
Yes. Okay.
I thought so because I mean it's terribly more difficult to do the sound radiation and everything. So, my other question was about like related to the sound post and the thickness. So, for example, if you change the thickness, does it automatically change the length of the sound post, or you have to adjust the length if you increase the thickness, or is it the interval between the two plates that keeps the same?
Okay.
I don't know if it's clear. And if you change the position of the sound post, you automatically have to adjust its length, or how does it work?
Well, the answer is yes. Well, not so deep as you say, but we are calculating. Can you see my screen, my wall?
Yeah, I can see.
So we have the highness of the ribs here. This is the violin. This is the sound post. This is the sound post. And this is the bass bar.
Yeah.
Okay. So the highness of the sound post is this one plus this one.
Yeah.
So we calculate these values, well, all these values when the sound post is changed. Of course, it has some limits. So the limit is that the program is cracked. So in some points of the simulation, you can move freely the sound post without any problem. But if you change by 5 centimeters or 10 centimeters, well, it cracks surely. So in few realistic movements, it works through this algorithm.
So the model automatically adjusts the height, the length of the soundburst.
Yes, the answer is yes. It's very hard to change the arching profile and changing the bass bar position for the way that the finite element models are created. They have several volumes interacting one with the other. And then you cut the part that you don't want. So it's very hard to control it. But you can move it in realistic ranges without problem. Yes.
Yes, and I put it in the discussion in the chat window, but yes, I would love to collaborate with you on doing some sound experiments and listening tests, and yeah, with your model and see whether that, for example, I have plenty of ideas now that I see your model that we can talk with the Bilbao team as well, how we could use your model to predict or see how much it agrees with what we have in the violins.
The model born to this situation. I hope that anyone can use it. Please do that. Thank you.
We keep in touch.
All right, back to Joseph Najibari.
Your analysis, Jesus, was restricted to the 4 main peaks of the signature mode. However, all violins have emission also around 1000, between 900 and 1200, including the original Titian has a relatively strong peak there. So as George Stopani correctly said, it's not only the location of the peaks, but the amplitudes really matter. We have made a copy of the Tiziano, and all the modes were about the same, but the peak around 1000 was way too high. So I wonder, how do you control, or how did you control the amplitude of emission around 1000 in your violins, which seems to me surprisingly low, and I consider this a benefit. So what was in your method of computing with a finite element method to achieve this end, to have low emission around 1000? Or did it come spontaneously?
Yes, that's correct. I must warn that the 1 kilohertz words in this talk was only very preliminary results. So, as I previously said, we changed a lot of parameters. Let me show you a paper. I am doing this right now. Even it doesn't have figure names. In this bridge mobility, you can see the original response of violin 1 in the black line. And the green line is taller, a higher bass bar. And the blue line is lower bass bar. But you can see that the black line is not the average of both situations. I don't know why. I was expecting that it was changing by steps, but this is not true. We have three configurations of the bus bar and 3 very different behaviors in the 1 kilohertz frequencies. So the answer is I don't know. It's very, very hard to me to obtain one conclusion about the bus bar linked with the 1 kilohertz region, the transition field. Okay.
Well, I think this is not only my problem with my Titian copy. There are many makers who are confronted with the same problem, that the amplitude around 1000 is higher than the amplitude of B1 plus. And the sound is nasal or unpleasant in a certain way. So maybe you could look into that problem with all the stuff you have and your interest and time available. I would be glad to hear from you again about this.
Yes, of course, my goal is to publish a good result about this. Pushed for some rejections previously in the process, but it brings me to this situation. Of course, it will be free for everyone. Thank you, Joseph.
Thank you.
All right, Don.
Yeah, on the material properties used for the finite element model, particularly the spruce, is there any accounting for the drop-off of properties with the slope of the surface? Particularly the cross grain of the spruce above the F-holes. It would really drop off severely with the angle of the arching.
Well, the answer is that we take very basic values of the wood. The best results, obviously, will be to take the elastic properties at every part of the whole model, of the whole plate. And you can see very different behaviors with how the wood was cut. But this is in practice, at least for us in the workshop, and to preserve these samples in a small bag, and with a label saying, well, what is the violin of these samples, is very, very useful in the classroom for the students. So while it's better to measure in every part the material properties of the plate, collecting the samples with the measurements of the generic or an estimation of the material properties is very useful in the future. In the future, when you are analyzing an instrument. So all my students has these samples for all his violins. So in the history of the school, when I take a violin, the first thing that I want to say to do with the violin, of course, is playing, and the second information that I request is the density of the wood. So the answer previously was, I don't know, but now the answer is, let me show you the bag with the samples. So we have some advantage of this very basic process done, okay? The answer is no, we don't measure in any part of the plate.
That's sort of what I expected. It's very complicated how the properties of the wood change with slope. So I didn't expect you would do that. But just one other comment regarding what George said earlier about the signature modes don't really tell you that much about the character of the instrument. Just this week I did an experiment taking off a maple back and putting on a back made out of medium density fiberboard, really crappy material. The B1 Plus dropped about 50 hertz, but still playing it, it seemed pretty much the same instrument. Just in the lower strings, a change in the fullness and a little bit in the playability of it. But the general sound character was pretty much the same.
Totally agree with you, totally. We tried in my first years of this career in violin making, we tried to improve violins, removing the plate and changing the bus bar and doing a lot of things until reaching the conclusion that you say. When the violin burns, he will sound in one way forever, at least in my experience. If you want to do a violin with dark sound, to change to a violin with a very brilliant sound, I think you are wasting your time. The violin will be dark all his life and brilliant all his life if he, well, it born in this way. Totally agree though.
Yeah, I'm all for the finite element models and being able to test differences by changing geometry or material properties, but it's really hard.
It's not so hard. We can do that. Maybe in the future we can schedule one session to show that it's not so complicated. I'm hearing the voice of Pantao saying that it's not complicated for you, but it's not the same reality for the whole world. But hope so that you can use it. Perfect. Thank you, Don.
All right, Jim.
I've actually follow-up comments on both of the previous questions as it happens. So on the thing Don Noon was saying, just to my slant on that, which I think may make sense to the makers, I think what you are simulating in your model is probably a top which has been pressed rather than a top which has been carved. You've got a cross-grain stiffness which is the same and follows the arching round, which is what you'd get if you did the Bill Fulton thing of pressing your spruce into shape rather than carving it out of the solid. So you've done something which makes sense to a violin maker, but it's not what they usually do. Don is absolutely right that the properties do vary enormously with grain angle. I mean, if I remember the numbers correctly, 10 degrees off the quarter is a factor of 2 in the cross-grain stiffness. So the slope is indeed steep enough that it matters. But on the other hand, Colin's results rather suggest that certainly down in the signature mode frequencies, as he already said earlier, arching dominates everything. And even the material properties I mean, Colin managed to get surprisingly good results with isotropic plates because the arching dominated things and switching to orthotropic material made surprisingly little difference. It surprised me. So there is an important issue there, but probably your model is fine. And say it may help the makers out there to think in terms of the model being a Bill Fulton pressed top rather than a bent one, rather than a carved one. Just on the other thing, because of the question came up about to what extent do you govern the character of instruments by the signature modes? Just to relate a little experience, something we did some years ago, some people will remember this experiment, we actually had a little grant and we got, back in the heyday of plate tuning and Carleen Hutchins and all that, we had 6 violins made by David Rubio, who was a local violin maker in those days, which were all based on the same model, same arching, matched wood and all that, but he deliberately varied the plate tunings. over a pretty wide range in terms of the sort of Hutchins, you know, from a bi-tri-octave super high frequency down to something that she would have said was hopeless. So we got these 6 violins. I still have some of them, and we have lots of time spent playing them. And the typical reaction of players, so these are instruments that had their free plate modes and to some extent their signature modes varying about as widely as you realistically can while still making something that seems to be a violin. The reaction of most players, and I think Fan has played these, Colin has played them, is that basically they all sound like Rubios. So the character of the maker, the things that he was keeping constant and that he always did, his model, his arching, his wood choice, somehow came through, and the character was, there were detailed differences, you can tell them apart, but there was something in the character of the instruments which led people to say they all sound rather like Rubios. So it's a data point to support what was being said, that signature modes are only part of the issue. And if only we knew what the other things were, we could measure it. Thanks.
Yeah, but trying to tune the signature modes is the first approach to trying to solve this situation.
Oh yeah, no, I wasn't criticizing what you've done. It's perfectly sensible. It's just that someone raised this issue that signature modes are not everything, and that is also true.
Yes, in fact, if you filter the signature modes region in a violin in the sound of a violin, all the people will recognize the sound of a violin, even if you are only playing from 600 hertz for higher frequencies. So it's a very hard task. And with your comment about David Rubio, I am thinking that his particular way to obtain the arching profile could be not changed too easy. Maybe for one violin maker, the way that they are removing wood, it's very determinating from the final sound of all his or her instruments. So it's a very great comment. Thank you, Jim.
All right, Claudia?
Yes, talking about the arching, when we built the Bilbao violins, we had this comment of Jim in mind, because I was there when you played the Rubio violins, and I realized as well that they were very similar. And so when we built the Bilbao violins, we thought, okay, let's try to have more violins built by external makers to see whether it will increase the variability, because I was a bit worried that the 6 violins being built at the Bilbao school, even with very different thicknesses, may end up very similar, a bit like the Rubio violins. But that's actually not true. The 6 violins, the 6 Bilbao violins are very different, and there are clear differences in their timbre, some being really disliked, some being very liked, being considered as very, top quality violins. So even with the same arching, you can end up having quite some variability by playing with thicknesses, even if you try to keep everything else constant. So yeah, so arching does play a role, but the thickness of the place will do play a role as well, more than maybe we would have thought it would.
In fact, in one of your talks last year, Claudia, I tried to ask about the arching profile of your violins. But I think that my question was not so clear because let me show you now. Now I have this opportunity. I need to use this opportunity.
The arching profile was Uberman, the Strad Uberman, and it was fixed by CNC machine. So it's the same for all violins. The makers were not allowed to touch the arching. They were not to touch the outside surface of the violins, of the plates.
So
evaluated through inside.
my question today is, you have the bridge mobility of your 6 violins. Well, it's pretty easy to obtain. This is frequency.
Yeah.
And you are trying to locate differences in the profile of the response to link these differences with the thickness of the plates that you create in your violins. For example, here and here, well, in this example, we can see the difference. But you have violins with the same arching profile. So my question is, have you found the same behaviors in one part with the same behavior in one part of the response? Because maybe it could be linked to the arching profile. It was my question, Suchade. It is possible to link arching profile with some similarities in the 6 bridge mobility of your violins? Well, maybe
so yes, you would like to link the arching profile with the similarities in the response. I mean, that's still an ongoing work because you would like to look at the similarities and as well look at the dissimilarities, which are due to the thicknesses. And ideally, I think to really be able to answer the question, we would need to build another set with a different arching profile and experiment. And then we would have 2 sets, you know, with 2 different arching profiles, but the same variation in thicknesses. But we need money and time. So,
yes.
But we do, I mean, we are planning because as George wrote in the chat, we have everything. We have, you know, all the model analysis of the different plates during the different steps of graduation, and we have the model analysis of the corpus before, just after being assembled, and then the full violins, you know, so there are plenty of data to look at. For now, we have dedicated most of the work to the perceptual tests to see what we can get, and we've made some progress, and that's what we were going to present in a next talk in probably September. Okay. And by that time, I hope we will have made some progress as well, linking these properties with some of the measurements. But even in listening tests where we thought it was very difficult because they all sounded like violins, as you know, when we do listening tests, there are actually very clear differences, much more than what I thought it would, because the test is very difficult. You hear 13 violins, you know, and actually people really heard big differences. So big, I mean, relative to the set of, you know, 12 violins. But so hopefully we will be able to correlate some of the perceptual properties with some of the measurements, and hopefully we can then relate that to differences in the thickness of the plates from the start and similarities in terms of arching. But but I think maybe your model with this could help, because we could maybe test some of the hypotheses. So even if it's not the same arching, you know, if we realize some similarities with our violins, do we get some similar similarities with your model? You know, even if it's a different arching. I don't know to which extent we can really do some links. And
I have a problem to do that. I have a problem to do that, because if you are changing the arching profile, of course, profile of the bus bar is changing too. So not only the arching profile is changing, but maybe without bus bar we can do that. Maybe we can remove the bus bar quickly, because this is a problem. I mean, in the workshop is 100 times harder.
Yeah.
Yeah.
With your model, you can keep the arching constant and you can modify the thickness. So we could possibly simulate a bit what we have done with real violins and see how much you what are the changes you can observe when you simulated violins, and how similar they are to the changes that we can observe?
Maybe, as you say, with money and time, we can we can modulate your violins. It will be great, because now we have a real instrument, and in this beautiful world, could make a simulation of violins, and the calibration process could aid a lot. But maybe in the future, of course, with money and time. Yes, it's a great word. Thank you, Claudia.
All right, let's go to Colin.
Can I return, in fact, to the business of quality and frequency range over which it's important? It's very interesting to listen to recordings, for example, before 1925, when the limit of the frequency response was only about 2.5 kilohertz. And you listen to Chrysler playing on the most wonderful sounding instrument, recorded in 1911. And it sounds like a wonderful instrument without, in fact, top and almost no bottom either, because you couldn't get the low frequencies on low recordings. You're relying entirely on the function of your ear, putting those frequencies in from the various harmonic potentials. But the important thing is that there's by the time you've got up to 2.5 kilohertz, it's sounding really like a violin. Up to a kilohertz, it doesn't sound like a violin. It sounds like some sort of woodwind, almost like an on martinon in sound. So what is terribly important, to my mind, in the sound of the violin is what's happening between around about a kilohertz up to about 2.5. Obviously, the brilliance of the violin and the cutting edge of the violin will involve the higher frequencies as well. But you've got the full character of a violin sound by the time you're easily up to 2.5. So what was being said before about the lack of output by Joseph, in fact, in the transition mode region, for example, is actually relevant to the sound of the violin. And I think we should be thinking much more about what the output, and we're talking about the audio output, rather than the way the violin vibrates in that range, which we now call the transition region, into the lower end of the bridge hill, because that's the area that I believe, from evidence, that it gives you the quality of the violin. The sheer fact that you're listening to a violin rather than another instrument.
Well, you start your comment saying, talking us about some recordings from the first years of the 20th century. Huh? Okay. And I was remembering my classroom yesterday, reading the book of Bukur, citing a text of Julian Mayer, which is in German. I don't have this paper, but he say, she's saying to us that Mayer found that the player and the playing parameters are determinant for the overall tonal quality of violins. Well, you say that the proto-violin was played and it sounds like a violin. Yes, something like this. So involving sound recordings is in, I don't know if this is the best way to begin to understand the sound of the quality of the violin.
I'm not arguing that we should use sound recordings to do so. I'm arguing that in order to get an instrument sounding like a violin, it's the frequency range between a kilohertz and 2.5 kilohertz, but it must be involved, because if you listen to Chrysler playing, it sounds as though he's playing a wonderful instrument. Agreed, it's the artistry that gives you a feeling that it's a great player playing, and it's a lovely sound, but it really does sound like a violin. And that almost certainly has very little in the signature mode regions, nothing above 2.5 because there's nothing there. And so that the quality of a violin, to my mind, is very much associated with that frequency range. And we ought to be paying perhaps more attention than we have in the past. The signature modes are easy to measure.
Yes.
And they characterize a violin in a certain sense. That's why they're called signature modes. But really, if you're looking at quality, I do believe that we really ought to be looking at the higher frequencies from where it becomes important acoustically, because there's a great big dip at 800 hertz, whereas your measurements were showing quite very strong outputs. But if you look at the actual sound output, it's quite low there. It comes up quite rapidly towards the kilohertz. And then, of course, we get these broad hill regions. But I'm saying that it's those lower regions that are very important in determining the sound of the violin.
Well, Colin, I know of at least one violin maker who has spent a lot of time in the past years concentrating on that very region you're talking about. So, so I think there is certainly violin makers who are working consistently with your theories about
it's not my theory. It's an observation.
Okay, but actually, since I have you, Colin, because I think you and Jesus are the ones to answer this question, because I don't want to neglect the question that was asked almost an hour ago in the chat line. So the question is, can you further comment on the contribution of the violin ribs to violin sound, all related to your finite element analysis results?
Yes, well, no, I can't do the correlation with the sounds because it doesn't exist, or no evidence does. But the ribs certainly play an important role. An important role because they they're the primary source, which people often don't realize, between the coupling of the top and the back plates. So certainly in the signature mode region, it's important. They play much less of a role in the radiated sound at higher frequencies, which is largely determined by the way that the plates vibrate themselves, top plate and back plate separately, and even the upper bout and lower bout separately. They have sort of rather localized modes, which are all radiating. And they leak out into the ribs a bit. And so to the extent that they leak out, effectively changes the area of the top plate and back plate by leaking out just a little bit. That's all the ribs do at high frequencies. And so the ribs are undoubtedly important in the acoustics of the violin, but the correlation, well, I would say that having ribs essentially makes the top plates and back plates seem a little larger at high frequencies from the acoustical point of view. So it's rather light. If you want plates that are more flexible, for example, that's making the waves get out a little bit further and therefore radiate more strongly. And the radiation gets increasingly important of the waves around the edges of the instrument. So it is important because there's a cancellation of the waves because some of them go up and down in regions, but it's the ones at the edges mostly that radiate as you get to higher frequencies in the intermediate range. And so in that range, it may well be that the strength of the ribs is important. And I mean, one of the things is that, of course, as we go to the larger instruments, the ratio of the rip height to the plates changes. And that may well be one of the factors giving the different timbre, in fact, that tells you that someone's playing on a cello rather than high up on a violin, you know, when they're playing in the same notes. The other way around, actually. High up on a cello and low down on a violin. They sound different.
Mm-hmm. You have anything to add to that, Jesus? About the ribs?
I was in the bathroom and I'm reading all the questions. I don't know if for example, well, something asking about a method where he doesn't understand my words, but I don't understand the question. He said Dr. Torres spoke about robbing coin method. Does anyone know what the right name is? I don't understand, but maybe, but I don't remember to speak about the robbing while breaking technique, but this is the only thing that I can imagine. Well, right. I want to say that the do-it-yourself wrist mobility is using the robbing while breaking technique, which is
thank you very much. I found it already.
Oh, okay. Oh, Rob, you're here.
Yeah, roofing wire breaking technique.
Yes.
Was I found it in the meantime.
Okay.
So thank you very much.
Could you explain it to everyone else, please? Because not everyone else will recognize what the roving breaking technique is.
Okay, roving while breaking technique is used to drive big structures where impulse methods doesn't work, like buildings or bridge or big bridge. So instead of impacting the buildings, you pull it. You pulled
how do you attach it?
The answer is I don't know, but you pull the structure.
Yeah, yeah. I understand that violin.
Ah, with the violin. Oh, well, with a wire, we pull the violin from the bridge. Instead of hitting the bridge,
yeah,
we cut the wire and the violin seems like this.
Yes, right.
And that's all.
And but that's Jim Woodhouse's speciality. Roving, in the sense you can only do that at selected places. You can't do it on the plates themselves. Not unless you glue the wire on one end and pull it off. And on the whole, you can't do that with a valuable instrument.
We're still working on it.
So yeah, so typically the wire
I can think of a way of doing it. I can think of a way of doing it. What you do is you have two little magnets that are small on either side, which you can rove around, and then you have a wire with another magnet on the end. I mean, it's not non-invasive, it's not destroying things, but it's the one way I can think of that you could actually do a pulling technique on a plate.
Yeah, so it's typically just done on the bridge and on the string. You move the wire around the string, you know, one of the strings, depending on where you want to pull on the bridge, and you just pull. So I think I think it's just Colin that's experiencing some internet problems. We're losing part of.
Am I? Yeah, the reason I was not here before, because my landline coming in is corrupt, and we're waiting for outreach to deal with something. And so both my internet and my ordinary telephone doesn't even work.
Okay. All right. So we still have two hands up. Anders, I'm going to skip you since you've already had a couple of chances, and I'm going to give John Fable go. Let him go first.
Oh, what a great scene! I just wanted to make a thanks, Fan, and everyone for the organizing this. I'm all in on this monthly Friday. Fabulous. So I just wanted to make a comment on Colin's comments about sides, and my experience not with so much with violins in this regard, but with guitars. I found that by making very lightweight, flexible sides on smaller instruments, I can kind of cheat the instrument into effectively having some of the characteristics of what you get from a larger soundboard, but retain some of the relative efficiency and treble response you get out of having a smaller soundboard. So that's something that, and I've been working on characterizing that a little more objectively, but I also wanted to see how that might translate into violins, which of course are more complicated with corner blocks and things like that. But anyhow, just some observational comments. Thank you all. Fabulous.
All right. Anders?
Yeah, I only had a comment to what Colin was talking about with listening to old recorded music. One simple way to make an instrument sort of losing its low frequency power is to put cotton in the F-holes. And if you fill the instrument with cotton, you get even less input from the lows. And the surprising thing is that you keep much of the high frequency response of the instrument. So it was a surprise to observe that it wasn't all that bad. So every now and then you get experiences like that. For instance, thick instruments which is supposed not to be a good instrument, maybe turned out to be quite well functioning well as a Hardanger fiddle, for instance. Yeah, things like that. So there's many ways an instrument can be good and function and can be interesting to work with. And I think working with the same thing all the time is probably not so interesting, not even for a musician. So there might be several possible aims.
All right. Okay, we're approaching 3:15. I think we should probably wrap it up, unless there's some final questions that people are dying to ask. All right. So thank you everyone for coming. Remember, it's the first Fridays of every month, and next month, Professor Chris Rogers, one of his students, is going to present the OB app, and that's an application, a piece of software that Joseph Curtin has been using intensively for the past couple of years to do his measurements. And I think a couple of other people have started to use it as well. So Chris has written this app, and it's available for free, and he's going to introduce it and show you what you can do with it. So that's next month, first Friday, and Claudia is going to talk about the Bilbao experiments. We still haven't scheduled the exact month, but it's probably going to be September, as Claudia says. But we'll see. And in the meantime, we'll schedule some other presentations for future months. So stay tuned for the announcements. And thank you, everyone, for coming. Bye-bye.
Thank you, Fan. I want to see the comments quickly. Thank you, Fan.
When you record,